Hey everybody, what's up? And welcome back to the Sanctuary. I'm your host, Professor C, and today I'll be taking us through another A&P study session. Specifically today, I'll be talking about atomic structure, and we'll be doing some practice problems today to help us figure it out a little bit better. So, without any further business, let's get right to it. Okay, let's look at helium. I've been given some information right here about helium. 2 protons, 2 neutrons, 2 electrons. I know I can draw that like this. 2 protons, 2 neutrons, and the electrons are going to go out here in a shell. There's only 2 of them. I know that's what fills the first shell, so its valence shell is full with 2 electrons. Let's see if we can answer some questions now. What is the atomic number of helium? Well, I know that simply equals the number of protons, so 2. What's the atomic weight or mass? Well, I know that's the weight of the nucleus, or the protons and the neutrons together, so that would be 4. How many energy shells do we have here? Well, just 1. That's all we needed. How many valence electrons? Well, that is the valence shell. Since we just have 1 shell, it is the valence shell, and we have 2 electrons in it, so there are 2 valence electrons. Is this atom stable or reactive? Well, how do we know? Well, we look to see if the valence is full. In this case, the valence is full, so this is stable. It does not react because its valence is already filled. Electrostatic charge? Well, we don't have, more than 4 or less than 4. We're not even going to get into that with this one. And then is it going to lose or gain? Well, it's not going to do either because it's stable. And again, this is why we don't talk about stable atoms too often in a biology class, because they're boring. They don't do anything. And you can't really discuss any other properties because they don't do anything. So let's try some now that are going to be reactive and see the difference. Okay, let's do boron now. Boron, again, given 5 proton, 5 neutron, 5 electron. What do? I draw a nucleus. 5 proton, 5 neutrons. Okay, great. 5 electrons, where do they go? Well, I need a shell. How many go in the first shell? Well, according to the octet rule, 2 go here and 8 go in all the others. So if I put 2 here, I need 3 more, right? Because I've got 5 I need to put on my picture here. And I've got 2 already. So I need another shell. And I'll just put 1, 2, 3, just to keep it easier to count. Okay, there's our model. And I'm telling you, even though I've done this a million billion times, right, I still draw the picture of these before I try to answer the question because it just helps. Atomic number. Well, I know that's the number of protons. 5. Atomic weight. That's the weight of the nucleus. So the number of protons and neutrons together, that would be 10. Number of energy shells. We've got 2 now because we filled the first. Number of valence electrons. How many electrons in the outer shell? 3. Which, remember, is less than 4. Is it stable or reactive? Well, it's reactive because its valence is not full. And in this case, how would we get it full? Well, we could take away those 3, or we could add 5. Which would be easier to do? Take away 3, right? So it's more likely to lose. And we know the rule, if you have less than 4 and you're likely to lose, you're considered to be electropositive. Okay, let's try another one. Oxygen. One of the big 4, right? So, same game. When in doubt, draw it out. 8, 8, 8 is what I've been given here. 8p, 8n. Boy, it's getting easy now, isn't it? After you do it 2 or 3 times, it becomes quite simple. And I need 8 electrons. So where do they go? They go in shells. And I know 2 can fit in this first shell according to the octet rule, and the other shells can hold up to 8. But I don't need 8 more, but I do need another shell. I need 6 more. Right, I need 6 more now because I've got 2 in the first. So I could put, there's 2, there's 4, and there's 6. And now I've got my Bohr model complete. And now we can answer the questions. If we've drawn the model correctly, we can use it as a reference. Let's see, atomic number. Well, that's the number of protons. That would be 8. Atomic weight is the weight of the nucleus of the protons and the neutrons, so that would be 16. Number of energy shells, I've got 2 surrounding the nucleus. When I look at the outer shell, the valence shell, I see it has 6 valence electrons. That would be more than 4. Okay, is it stable or reactive? Well, I know it's reactive because the valence is not full. And you may think to yourself, what would make it full? Well, I could give it 2, and that would give it 8 and be full. Or I could strip those 6 off, which would be easier, give it 2. So it's more likely to gain. And again, if you've got more than 4 in your valence and you're likely to gain, you're said to be electronegative. All right, let's do one more just for fun. Sodium. And sodium's one of those weird ones that has a Na for his number, or his symbol. And it doesn't have all the same numbers for its subatomic particles. It's got 11 proton, 12 neutron, 11 electrons. So don't get tripped up by that. Just draw the picture like you've been doing. We need a nucleus. We need 11 protons, 12 neutrons, just like we're given. We need 11 electrons in this picture. So let's start drawing some shells. First shell holds 2 and only 2 according to the octet rule. I need 9 more. Right, I need 11. I need 9 more now. Now I can draw another shell, but it's not going to hold 9. It can hold 8 according to the octet rule, so I'll draw them on here. But I'm lacking 1. I need 1 more. I need 11. I only have 10 in my picture. 8 and 2 is 10. I need 1 more, so I need another shell. Pretty big atom here, and it's only going to have one little guy in it, one little electron in it, but that's the way the model is drawn here. So if the model is drawn correctly, and it is, now we can start answering questions about the model. Atomic number here, well, 11, simply the number of protons. Atomic weight is the protons and the neutrons in the nucleus, so 23 would be the atomic weight. Number of shells, well, I got 3 shells now. I had to add a third one to put that lonely guy up there. Number of valence, just 1. I just got 1 here. And remember again, that is less than 4. Stable or reactive? Definitely reactive. Why? Because its valence shell is not full. How can we make it full? Well, very simply just kick 1 off, right? We could add 7, but that just seems way harder than just kicking 1 out. So he's likely to lose. And we know if you're likely to lose and you have fewer than 4, we'll call you electropositive. Great. Practice more on your own. You can make up these on your own and draw them out all day long if you wish, but that is how to solve questions about atomic theory. Now, somewhere along the road you may hear about isotopes. I will not be making a big deal about them ever again in my lectures, but I do want to go ahead and define them for you. So an isotope is a different form of the same element. Okay, notice here, there's a protium, a deuterium, and a tritium. Those are all hydrogens. How do I know? Because I see 1 proton, 1 proton, 1 proton. And that is the atomic number, 1. Hydrogen is 1. Hydrogen has 1 proton. Those are all forms of hydrogen. The thing is, the neutron number is different. This one has none. This one's got 1, and this one's got 2. So what you're looking at are isotopes of hydrogen. So another trick that I learned back in the day is isotopes have the same atomic number, right? 1 proton, 1 proton, 1 proton. That's atomic number 1. So, but the atomic weight here is 1, the atomic weight here is 2, and the atomic weight here is 3. So this is what really set it for me a long time ago when I was trying to figure this out. Isotopes have the same atomic number, but differ in how much they weigh because they have a variable number of neutrons. As usual, thanks for watching. If you want to see more, check out the other videos in the series, and bye-bye.